안녕하세요 여러분, 혜리입니다. So in this video, I'm going to start with complex numbers. And before you watch this video, I strongly recommend you to revise trigonometries first, because we will be using a lot of trigonometric identities and I will not be deriving them all the time, okay? So please revise trigonometry first, okay? So let's start with complex numbers. So this is where IB math gets more interesting. So let's see what it is first. Let's understand what it is first. So in the elementary math, we learned a set of number, which is the natural number, right? So natural number contains all positive whole number, right? So starting from 1 to like any positive whole number. And then next, what we learned is we learned integer, and we have also learned that natural number is included in the set of integers. So integer includes natural number and negative whole numbers and also 0, right? So this notation is used in set operation, so it means that a set belongs to the other set, okay? Now, after this, we learned rational number. So rational number refers to a set of numbers where a number can be expressed in a fraction form. So P over Q, where P and Q are both, so Q is natural number as denominator, and then P is an integer, so that's okay. And after this, we learned real number, set of real numbers, and for every functions or like log and exponential and trigonometry that we have seen so far, everything is defined in real number. Now, what we are going to look at is we are going to look at complex number, and complex number is the biggest set of numbers that you learn in IB syllabus. So by looking at this, we can see that the set of complex number includes the set of real numbers, right? So mainly, like what we had for integer, complex number is divided into two separate set of numbers. So real number that we know, and then pure imaginary numbers or complex numbers. So where can we find complex numbers? And let's see. So for example, a quadratic equation like this, and when we have to find the roots, we can use quadratic formula to find it. But before that, let's quickly investigate its discriminant. And in fact, the discriminant is less than 0. What does that mean? It does not have any real roots, right? Then does that mean it doesn't have any roots? Well, in terms of, so previously we only learned set of real numbers, right? That's why we said there's no root, so there's no real root. But now we learn complex numbers, so in fact this quadratic equation has roots, and those roots are just complex roots, not real roots anymore. So using the quadratic formula, this is what you will get. So we have this, right? So -4, right? So -4, that means -1 times 4. So if we can move 4 out, and then we can cancel that 2 with the 2 in the denominator. So this is what we have, and that means the roots of this quadratic equation is either -2 plus root -1, or x equals to -2 minus root -1. In complex number, we define -1 as I. So note that I is not a variable. Clearly it's not a variable. I is a fixed number. So it's fixed to root -1. So it's like pi or natural constant e, okay? So it's just a notation for root -1. So that means we can write these two complex roots using the symbol, right? So this is what we have. And for complex numbers, so we have a form like what we had for rational. So complex number can be written as a plus bi. So where ba is called the real part and b is called the imaginary part. And note that these two numbers a, b are real numbers. Okay? So let's quickly see some basic operations of complex numbers. So one thing that you can use as a tip is that just treat this as two different terms. So remember when we learned the basic algebra in elementary math, we could add we could either add, so for addition and subtraction, we could only add and subtract with the like terms, right? And then for those different terms, we couldn't do that, right? So what we can do for complex number is that, let's say we have two complex numbers like z equals to 2 plus bi and w equals to c plus di. Then first, what happens when we add the two complex numbers? So as I said, term by term. So this term has I, right? So that means it's the imaginary part, right? And this is the real part. So we just add the real by real and imaginary by imaginary. That's it. Okay? So that's the real so this a plus bi is from z and this c plus di is from w, right? So this is w and this is z. Okay? And with this new complex number z plus c, this is now the real part and this is the imaginary part. Okay? Then what about subtraction? So it's the same. So a plus bi minus c plus di, right? That means a plus bi, and same thing, what do we have when we multiply by -1? Then negative c minus di, like normal bracket expansion. Okay? So, and again, term by term. So real term and imaginary term. So this would be the real part of this new complex number and this would be the imaginary part. Okay? Then what about multiplication? So multiplication is also the same. So z equals to a plus bi and w equals to c plus di. So the product would look like this. And just do the normal bracket expansion that you did previously in algebra. So a times c plus a times di plus b times bi times c and plus bdi squared, right? Then here we have I squared, and what's I squared? In fact, I squared is just simply -1 because I is root to -1, right? So that means if we squared both sides, then I squared is equal to -1, right? So that means it's -1. So we have the real part as AC minus BD, and then we have imaginary part as AD plus BCI. So note that if we multiply two imaginary parts, then we will have a real part. Okay? So that's the real, and that's the imaginary. Okay? And not that important. So one last thing, just in case. So if you have a constant multiplied to a complex number, you can just simply expand it out as what you did for algebra. Okay, so very simple. So that's the very basic thing for basic operations for complex number. And note that we haven't done division yet, and because it's not the correct timing to do it. So we're going to do division later, very soon, okay? So now we're going to look how we can interpret complex numbers geometrically. So remember, for real number, what we had is that we had a number line or a number plane that contains all set of real numbers, right? And we have a similar thing for complex number as well. And instead of calling it as some like complex plane, we call it as Argand diagram. So it's basically a plane that contains every complex number. So how does it look like? It looks like xy plane, but instead of having x and y axis, we have the real axis and imaginary axis. Okay? So for example, if you want to plot for example -2 plus I that we have seen before. So here we know that the real part equals to -2 and the imaginary part equals to 1, right? The coefficient of I is the imaginary part. So that means the real part, and this will be the origin. So the real part will be -2, and then imaginary part would be 1. So this is where -2 plus I is located. Okay, and similarly for -2 minus I that we also had, that means this is where the point, the complex number is. Okay, then what about how expressing real number? Because remember that complex number, set of complex number contains real number as well, right? Then how do we express real number? Just on the real axis, so something like 1 or maybe pi. And what about just pure imaginary numbers, so where you don't have a real part? Then maybe something like here, right? What does that mean? That means 2i, right? And this is just 1 and this is just pi. So this is how we can see complex numbers geometrically. And using this, we can make another, we can get another form, we can define another form of complex number. So in IB syllabus, you will learn 3 forms. And probably those are it. So first is the first form is called the Cartesian form. So if you have done vectors already, then you can use, so it's similar to the Cartesian form of vectors. So a plus bi, or if you want to use something with vector, you can just call it as x plus iy. So just, you can use any variable, okay? iy or yi, same thing, okay? So yeah, so any complex number in this form is called the Cartesian form, okay? Then the second thing is that what we are going to learn using the Argand diagram. So it's called the polar form, and it's in this form. And lastly, we have Euler's form, which can be written like this, okay? So Euler form we're going to learn probably like much later, but still these 3 are in IB syllabus, so you'll have to learn all of them. And let's try to learn this polar form first. So note that we can always convert from Cartesian to polar. Okay, and also to Euler. So you can convert from here to here, or here to here, or here to here, here to here, anyway, okay? In any direction. Then we're going to learn polar form first. So let's look at what the polar form is. So the main advantage of using polar form is that we can get we can quickly get the geometrical aspect of a complex number. So let's see how we can convert the complex number from Cartesian form into a polar form. So R is called the modulus. So R is defined as root a squared plus b squared. And then argument is defined as, so argument refers to this theta, the angle, and it's defined as arctan b over a. And I'll tell you why we have these properties in the polar form. So let's use the Argand diagram again. So let's say A and B are both positive for convention. So let's say this is where A plus BI is, right? Then the polar form is basically showing the length of this complex number from the origin, and it's also telling you the angle from, oh sorry, it shouldn't be called x-axis, so it should be the real axis and imaginary axis. So it's showing the angle as well. So a plus bi can be written as root a squared plus b squared times cis arctan b over a, okay? Then you guys may wonder, what's cis? So if you take chemistry, HO, then you may have heard something called the cis bond, but unfortunately it's not really related to cis bond, okay? So anyway, so back to complex number, not chemistry. So this is A, right? And this is B. And we can try to write A and B with R and theta. How? Because that one we can kind of make it as a right angle triangle, right? With R hypotenuse, theta, and B as opposite, and A as the adjacent. Then sine theta will be B over R. That means B equals to R sine theta, right? And cosine theta equals to A over R. That means A equals to R cosine theta, right? So that means A plus BI can in fact be written as R cosine theta plus R sine theta I, right? And we have a common factor of R, so we can group it, factorize it by R, and then we have cosine theta plus I sine theta, and cosine theta plus, so this is very important, it has to be plus, okay? Cosine theta plus I sine theta can be written as R cis theta, okay? So please remember that the angle must be the same, okay? And this has to be plus, so CIS, cis, okay? So this is the meaning of cis, okay? So in fact, it means cosine theta, so we have the angle like that, so that means cosine arctan b over a plus I sine arctan b over a, okay? So that's how we can interpret, how we can convert from Cartesian form to polar form or polar form to Cartesian form, okay? So let's try an example. Let's see. So okay. Alright, so I'll just use this paper. So let's use the complex number that we had. So z equals to -2 plus I. Okay? Then first, if we want to change this to polar form, that means we make this into r cis theta, right? And we know that r is called the modulus, and it's basically the sum of the square of the real part and then the imaginary part, and then put a square on it, okay? And square root on it. So modulus should be root 5. And note that modulus should be positive, right? Because it's basically looking for the distance, okay? So distance cannot be negative, right? So it has to be positive. And for theta, so this one, I don't think it's gonna be defined. So yeah, you can use your calculator, and then so if you use your calculator, arctan -half, so that's -26.6, so around that. And one thing to remind you is that for complex number, we usually use radians. So we still use degrees sometimes, but mostly we use radians. So be familiar with radians, please. So I'm pretty sure we all know how to convert the degree into radian. Alright, if you don't know this, then you have a serious problem. So please revise on trigonometry first. So that's the angle that we have. So let's just use three significant figures. So -0.464. So therefore, this complex number in Cartesian form can be written as root 5 cis -0.464 as in polar form. Then how do we move from here to that? Well, simple. So remember that cis means cosine this angle plus I this angle, right? So cosine -0.464 plus I sine -0.464. So that means the real part will be this, and the imaginary part would be this, right? So just calculate that and it will give you -2, and calculate this, you will have 1, okay? So since we have rounded up the value, it will not give you the exact value, but if you use the full answer using the calculator, you will have this value, okay? So that's the example of converting the form by form. And very important example we are going to look at is something like this. So for example, let's say we have a complex number in a Cartesian form, but not like this, but something that looks very similar to the polar form already. So something like this, let's say. So, well, if we just quickly factorize it by 3, this is what you will have. So if we have to change this into polar form, what we have to find is that we have to find the modulus and the argument, okay? And one thing, so it looks very similar to the polar form, this polar form, right? But as I have been emphasizing, it has to be, in order to make it into polar form, it has to be plus, okay? Has to be plus. But for this one, we have minus, right? So that means we cannot make this into polar form directly. So then what can we do with this negative sign? So we can recall some of the properties of trigonometric functions. So note that cosine is an even function. So we all know what it means by even function. That means if the input is negative x, then it has the same value as the input of x. Okay? So that means if we have cosine negative theta, that should equal to cosine theta. Okay? And similarly, y equals to sine x is an odd function. What that means is that if we have f negative x, then we have negative fx, which is reflexive over the origin, okay? So, or rotate the function by 180 degrees to either to clockwise or anti-clockwise, okay? So, from this, what we can derive is that when we have sine negative theta, we have negative sine theta, okay? So, these two will be used a lot, very frequently in complex numbers. So please remember this, okay? If you don't want to use the properties of even function or odd function, although it's the easiest, you can choose to derive this from using compound angle formula as well. So you can let this as cosine 0 minus theta. So, okay. So you can make this as cosine 0 minus theta, which will be cosine minus theta, and then you just expand it out. So cosine 0 times cosine theta plus, right, sine 0 times sine theta. Then what's, oh, sorry, not theta, 0, 0, okay, cosine 0. So cosine 0 is 1, right? So 1 times cosine theta is cosine theta. Sine 0 is 0, so we don't have to consider it. So that means cosine negative theta equals to cosine theta, okay? And you can do the same thing for sine minus theta and you will have the same result, okay? Alright, then let's come back to this question. So for this one, what we can do is that we can try to put this negative sign inside, because first we have to make this to positive sign, addition sign, okay? So by making this addition, we can put this negative into sign, because there's no point of evaluating negative I is just a fixed root negative 1. We can't really do anything. Or you can make it to I cubed, but again, it will not be helpful at all, right? So first we do that, and we can use this property to say that it's simply sine negative pi over 8, right? And also using the property of cosine function, which is an even function, we can say that it's in fact this value. Okay, so now we can write this as 3 cis negative pi over 8, because we have cosine, I sine, and we have the same angle, and then we have the addition sign. So that's what we have, okay? So then this is how we can convert this Cartesian form into a polar form, okay? One more example we're going to try is this. So this case, we have a negative coefficient in the very front. So a lot of students directly go for this and say that the modulus is -10 and then the argument is pi over 3, but that's completely nonsense because, as I said, the modulus cannot be negative. Because again, what's modulus? So that's why you have to remember the definition, okay? Modulus is the distance of a complex number from the origin when plotted on the Argand diagram, okay? So basically it's looking for the length of a complex number, and clearly length cannot be a negative value, right? Then what can we do? So that means we shouldn't keep negative sign in front, so we put inside. Okay, and this is a bit problematic than this because it's a bit hard to remove this negative sign inside the angle and to find the common angle, right? So what we can have is that we can get a help from some trigonometric, it's not a formula, but it's a very useful tool in trigonometry to determine the sign. So what I mean by sign is that either plus or negative, okay? So remember, for this diagram, we know that from 0 to 90 or 0 to pi over 2, so sine, cosine, and tangent are positive. And from 90 to 180, only sine is positive. And from 180 to 270, only tangent is positive. And lastly, from 270 to 360, only cosine is positive. And from here, what we know is that both cosine and sine are negative, right? That means so we want to put this inside, right? So we want to remove this negative sign. So we have to find the value of the angle where it makes both cosine and sine negative, and this is the region. So this is the domain of the So this is the region where this argument is located at. So let's get some help from the graph. So first, let's quickly sketch cosine. So you don't have to spend too much effort in the sketch, because you just need a rough sketch and you just need to find the value of the angle. So pi over 3 is somewhere like this. So although pi over 3 is a special angle, so you should know what cosine pi over 3, right? So that's cosine 60, so it should be root 3 over 2, right? But let's say you don't know what the value is. Then for this one, we can use the symmetry. So note that we are looking for the part where the angle is between 180 to 270, which is here, this part, right? And then we want to find the value of the angle that yields the same value as cosine pi over 3, but just the opposite sign. So that means using the symmetry, right? So, but this is not what we're finding, right? This is what we're finding. So that means this will be pi plus pi over 3. So 4 pi over 3. Okay? So that means at cosine 4 pi over 3. So what this means is that cosine 4 pi over 3 yields negative cosine pi over 3. Okay? And let's do the same thing for sine. So for those who can't really see this, so this is what I have drawn, okay? So this particular point is pi plus pi over 3, which is 4 pi over 3. And by looking at the graph and using the property of symmetry, we have cosine 4 pi over 3 as negative cosine pi over 3, okay? And doing the same thing for sine. So again, this is the region that we're trying to look for. And then also, just in case where we don't know the angle, so when the angle is not in a special angle, we can use the symmetry of graph to find the value, so find the angle. So again, we are trying to find the angle between 180 to 270, where it has the same value of pi over 3 but just the opposite sign. So that means basically we're looking for this value, right? And what is this? It's in fact the same as what we have found for cosine. It should be pi plus pi over 3, so 4 pi over 3, and we know that sine 4 pi over 3 equals to negative sine pi over 3. Okay, so that means, oh, and for those who can't really see well, so this is what I have drawn. Okay, so that means from here what we can do is that instead of negative cosine pi over 3, we can write it as cosine 4 pi over 3. And then also instead of writing negative sine pi over 3, we can write it as plus sine pi over 4 pi over 3, and we have I. So that means it's 10 cis 4 pi over 3. Okay, so the argument is 4 pi over 3 and the modulus is 10. In order to speed up, so you see that it actually takes quite a lot of time. So what I would recommend you is that quickly find the region that you're supposed to find. Okay, so remember that the both values of cosine and sine are supposed to be negative, right? So quickly find the region, and then just quickly use the symmetry. To be honest, this is the proper method of solving this, but if you really don't have time, then you can just skip this graphing part, and then either you can use the butterfly model diagram that some teachers teach you, but personally I recommend you to use graph. Okay, if you don't have much time, then well, sorry, but good luck. So that's why in the practice, so before your exam, you should do enough practices with this symmetry so that you can quickly analyze the graph. Okay, so that's it for converting from polar form and Cartesian form. Alright, and we move on to the next one. Not the Euler form, but some special things with complex numbers, so called complex conjugate. So I'm pretty sure if you are in chemistry, if you take IB chemistry, you have heard the term conjugate. So in acid and base, right? Conjugate pairs. So it's very similar. So when you have a complex number like a plus bi as in Cartesian form, then the conjugate of z has a notation like this, and it means a minus bi. So the real part stays the same, but just that the imaginary parts have the opposite sign. Okay? Please be aware that some textbooks, they use this z bar as the notation, but just note that these two are the notations for conjugates. Okay. All right, and we call z and z star, so I'll use z star. Okay, z star as conjugate pair. Okay, then what's so special about conjugates? Okay, it will help a lot in some calculations. And also when you have to find some properties of complex numbers. So for example, if you want to find the real part of complex number directly, then what you can do is that you have this formula, and why? Very simple to derive. So note that z plus z star is a plus bi plus a minus bi, right? So which is 2a. That's why if we just have the sum of z and its conjugate, we will have a, which is the real part of z. So this one, it means real part of z, okay? Second thing, what if we want the imaginary part? Okay, then we can simply do the similar thing. So this is how we can find the imaginary parts directly. And again, the proof is very simple. Z minus z star would be a plus bi minus a minus plus bi. So note that z star is a minus bi, right? But we have negative sign in front, so it's negative a plus bi, which yields 2bi. So note that if we divide this by 2i, then we will just have b, which is the imaginary part of z. So this notation means imaginary part of z. Last one, very important thing. So let's say you don't want a complex number, and in what case so what kind of cases am I talking about? So for example, let's say you have a complex number in a denominator. And let's say you don't want any complex number in the denominator. So you want to make the denominator in real number. Then we can use this third formula, which says that if you multiply z and its conjugate, we have the modulus of z squared. And again, the proof is very simple, because z times its conjugate, that means a plus bi, times a minus bi, right? And we already know how we can multiply complex numbers from the basic operation. So it becomes a squared plus abi minus abi minus b squared I squared, right? And these two intermediate terms cancel. And remember, I squared is -1. So that's a squared plus b squared, which is the square of its modulus. Okay, so very simple. Not a formula, but so this is the definition of conjugate. But what if we want to find the conjugate of a complex number when the complex number is in a polar form? So just use what we know. So conjugate means real part stays the same, and only the imaginary part becomes the opposite sign, right? So if this was negative, then the conjugate would be plus, and this is plus, so the conjugate is negative, okay? So polar form means r cis theta. Then why don't we just change this into Cartesian form? How? Very simple. We already know it, right? R I sine theta, right? Then the conjugate of z would be r cosine theta minus ri sine theta, right? Because the real part doesn't change, right? only the imaginary part becomes the opposite sign. So if we want to change this back to polar form, so we first factorize this by r. And remember, using the properties of cosine and sine, we can make this into minus theta plus I sine minus theta. And the reason why I'm also changing the angle for cosine is because the angle must be the same, right? So the only way to make this subtraction symbol into positive addition symbol is to put negative to sign, and then this is what we can do. So it can be written as r cis minus theta. Okay, so that means if you have a complex number z equals to r cis theta, then the conjugate would be r cis minus theta. Okay, so this is what we have, and some important formulas that you can use. So if you have an addition or subtraction of two complex numbers, and if you're asked to find the conjugate of it, then you can just directly solve for the conjugate, the addition or subtraction of the conjugate of those two complex numbers. And why? So the proof is again very simple. So let z be a plus bi and w be c plus di, where z and w belong to, of course it will belong to complex number, right? So we start with left hand side first. So left hand side, so let's consider the plus case, addition case. So that means a plus bi plus c plus di, conjugate, right? And a, remember the basic operation of complex number. So the conjugate means we leave, so the real part doesn't, so it does not affect the real part, but the imaginary part becomes the opposite sign, right? So this is what we have. And in fact, this is a plus c minus bi minus di. So a minus bi plus c minus di, which is the conjugate of the two complex numbers that we started. Okay, so it's the same for subtraction. Okay, and using this similar idea, you can also prove this, where you can distribute it like in exponential. The third property is it's very important. So for example, so everything here is important, but the reason why I'm emphasizing 3 is because it's a division of two complex numbers. And in order to do this, what you can do is that, so z over w, so if we use the same thing, okay, for this one I'll prove it for you. So let z be a plus bi and w be c plus di. Okay, then z over w would be a plus bi, will be a plus bi over c plus di. Then how do we find the conjugate? That means conjugate of this complex number, right? But it's not in the form of real plus imaginary part, right? That means we should try to make this fraction into a form of a Cartesian form, just normal Cartesian form. And how do we do it? How do we do it? We apply this rule, this formula, because we know how to change a complex number into a real number, right? So for this number, what we can do is that we can multiply the conjugate for the denominator. And of course, we can't simply just multiply to the denominator because that affects the equation. So we multiply to the numerator as well. And that will give you c squared plus d squared directly. And what about the numerator? We have AC minus ADI plus BCI minus BDI squared. So that means AC plus BD plus BC minus ADI over C squared plus D squared. Then the conjugate of Z over W would be, so the real part stays the same, but the imaginary part becomes the opposite sign, right? So this is what we should have, and you can confirm it by finding this using the same idea, okay? So it shouldn't be hard. And the fourth property, we have this, and this you may not be able to prove yet. You have to learn something called de Morse theorem. It's very hard for me to pronounce this, so later when we have to learn this, I'll use the way how, I'll just call this in how in the Korean textbook, okay? We call it as de Morse theorem, de Morse. So I'll use that pronunciation, okay? So that's it for conjugate pairs, and we have just seen like the basic properties of complex numbers, and we're going to look at one of the applications. Alright, so the first thing that we are going to do is polynomials with complex roots. Okay, so let's see, for example, cubic function or cubic equation. So you should probably have finished looking at the general shape of cubic equation or cubic function. So cubic function has three cases where it has one real root, right, and two real roots, but I'll sketch it one by one. So for one real root, that means it can be three repeated real roots, right? Something like y equals to x cubed. So that means the root 0 has been repeated 3 times. So it has a point of inflection. Remember that if the root is repeated 3 times, it has a point of inflection. If it's repeated twice, we will have a tangent, right? The graph will just touch the x-axis, but I'm going to talk about that later. But we also have a form like this as a cubic function. So something like, let's say, x minus 1 and x squared plus 4x plus 5. Okay, actually x plus 1. So one real root, right, from x plus 1. And we already know that this does not have any real roots, right? So just one real root. And the second case is when we have two real roots. And this is the case that, as I said, so one real root and two repeated roots. So something like x plus 2 and x minus 1 squared. So remember that if the roots are repeated, that means repeated twice, that means it just touches the x-axis, okay? Last case is where we have three real roots, and this should be very simple, right? So something like x plus 3 and x minus 1, x minus 2. So 3 real roots, okay? Then let's observe these three graphs. How many roots do we have here? So all of you, not all, but almost everyone, would say 1, right? Because we see 1 root. But in fact, there are 3 roots. But those 3 roots are just repeated so that it looks like it has 1 root. And this one, we have 1 root, but 1 real root. And we clearly know that we have 2 complex roots, right? And for this one, again, it seems like we have 2 roots from the sketch, but we have 1 distinct root and 2 repeated roots. So total, we have 3 roots. And lastly, we have 3 roots. So that means a cubic function, no matter how it looks like, it has 3 roots. But it's just that either it's just repeated or it's just complex roots, okay? So we have a fundamental theorem of algebra. So it says that a polynomial with degree n has exactly n roots, but some may be repeated. So it's a cubic function, that means the degree is 3. So that's why we have 3 roots. But for some cases, the roots are repeated, okay? So we have 3 roots for this case too. Just that we just have 1 real root and 2 as in complex roots, okay? And a very important property of complex number we have is that if, so let's say, if z is a root of a function where z belongs to a complex number, so z is a complex number, then the conjugate of z will also be the root of that function, okay? So that's why we cannot have a case for 3 complex roots, because if one complex number is a root, then its conjugate must also be the root. So for every polynomials that we see, there must be even number of complex roots. There can never be odd numbers of complex roots, okay? So that's the example. That's the main thing that we have to remember from here. And also, you'll learn this. This fundamental theorem of algebra is also very important. And you will learn this if you take IB Further Math and in linear algebra, or if you're planning to go to any like engineering, or if you want to major in engineering or mathematics or some physics, then you will have to take linear algebra in the university, and you'll learn a lot of things about fundamental theorem of algebra when you have to learn something called eigenvalue and eigenvector. But that's not the case, that's not the story for us yet. So let's try to use an example of what we just learned. So let's say we have a function with degree 4. And A, so show that I is a root, and B, find the other roots. So A, so to show a number is a root, is we just need to evaluate this, right? So we just need to check whether fi equals to 0 or not. So we don't know yet, right? That's why we have to show. So don't write it like that directly, just evaluate first. So I to the 4 minus 5i cubed plus 7i squared minus 5i plus 6. So I squared is negative 1. That means I squared squared will be negative 1 squared, so it will be 1. I cubed, that means I squared times I. So negative 1 times I, so that will be negative 5i. And we have negative 7 here and negative 5i and plus 6. Oh, but remember we have negative sign in front already, so that I squared will make it plus, okay? So please be careful with this calculation error. I also make a lot. So 1 plus 6 minus 7 disappears and 5i minus 5i disappears, so it's 0. Therefore I is a root. B. Find the other roots. So a complex number I is a root. Then the conjugate of I must also be a root. But what's the conjugate for I? Because it doesn't look like a Cartesian form for some of you, right? But I is certainly in Cartesian form because I is in fact 0 plus 1 times I, right? That means so if we call this as Z, then the conjugate of I would be negative I, right? 0 minus I, so negative I. That means I and negative I are the roots, the complex roots of this degree n polynomial. So that means first, using the fundamental theorem of algebra, we know that this has 4 roots. We don't know whether the roots are repeated or not, but first it has 4 roots. And the very first coefficient of the highest power is 1. So that means this, if we could factorize this, we will have this as in 4 roots. And we know 2 of the roots, right? One is I, so x minus I, and the other one is minus I, so x plus I. And then we just need to find the remaining 2 roots. And how do we find this? So we've already learned from the very beginning chapter when we learn factor theorem and remainder theorem. So we can find x minus c times x minus b by dividing this by this. So we need to find this first, right? So x to the 4 minus 5x cubed plus 7x squared minus 5x plus 6 and divide by this would be x minus c times x minus b. Okay, and this is assuming that x cannot be I or negative I, and that makes sense because so otherwise we cannot divide by this, right? So first let's divide this, and then we know that x minus I and x plus I, so it's a product of square, difference of squares. So it's x squared minus I squared, which is x squared plus 1. So basically we're dividing this by x squared plus 1. So we have x squared, x to 4. So 5 minus x cubed. So remember, we are not subtracting these two, we're subtracting this two because this has a power 2, right? So plus 6x squared minus 5x plus 6. And then we have negative 5x. So minus 5x cubed minus 5x. So again, we're not subtracting these two, right? So we have 6x squared plus 6, and then that's just 6. Therefore, this function fx can be written as x squared plus 1 and x squared minus 5x plus 6. So the remaining roots, those 2 roots would be 2 and 3, right? Therefore, we have plus minus I and 2 and 3 for the roots, okay? So, oops, maybe you guys couldn't see it. So that's it for today. So we have done the very basic concept for complex number. and very simple operations. And then we also learned two forms, the Cartesian and polar form. So please be aware that the deeper you go with complex number, the more trigonometric identities you will have to face. So please note that if you don't remember, or if you think you have a problem with understanding this use of trigonometric identities or properties of trigonometric functions, then please study complex number trigonometry chapter first. Okay, so that's it for today, and in the next video I'm going to talk about another applications, and I'm going to start the actual interesting properties of complex numbers. Okay, that's it for today, so see you guys in the next video. Bye.